But you can easily see that the concept of invariant mass can be extended, no problem, because P will still be, P square will still be equal to P1 plus P2 square, but this is just the energy momentum conservation equation. So for P1, I can replace it again by applying energy momentum conservation. That will be P3 plus P4, and this will be P5 plus P6. And this quantity is called the 4-particle invariant moments. That is the final state here, because these two are also unstable, made of 3, 4, 5 and 6. So this is the invariant mass of the final state. So the concept of invariant mass can be extended to multi-particle systems. But if they come from a single particle, the origin is a single particle, then this invariant must also be equal to the square of the mass of the original particle. And this is what you are seeing in the lower slide. It says that you will have lots of 4-particle things. Now, like the continuous distribution in the previous slide, you will get a continuum of what we call background, that is uninteresting 4-lepton events. They do not show any peak, any particular characteristics. But we see 2 bumps, and this can be understood as one bump is coming from the Z boson. That is, if you produce a Z boson, in fact 2 of them, then they produce 4 leptons, because each Z boson can decay into a lepton-antilepton pair. And the Higgs boson can decay into 2 Z bosons. Unfortunately, this will come later on. And each Z can decay into 4 leptons. So you will have a mass peak here, which is again at 125 GeV. So here a Higgs decays into 4 leptons, and the invariant mass is peaking at the mass of the Higgs. Again, there is a width, as you can see here, and this is another channel of discovery. But still I have not identified the Higgs boson. We have seen something, some new particle with mass 125 GeV. In fact, the second experiment confirms the first one, because we are seeing the peak at a particular mass. And the theory says that Higgs boson can decay into 2 Z bosons, and the Z bosons decay into 2 leptons, and that gives you a mass. Now the trouble, however, is the following, that still it doesn't tell you that this is the Higgs boson. So you have to do a little more quantitative thing. Now, as I told you that there are 2 probabilities. One is the production probability, a measure of which is the cross section, and the other is the decay probability, a measure of which is the width, right? So we go into that and we find the following. What is it? Well, as I told you, this gives the cross section. This is of course theory. If standard model is true, then we have these plots of cross section. What is this? This is the cross section in picobarns. To put things in perspective, I tell you that 1 picobarn is 10 to the minus 12 barns. And a typical strong cross section, which is easy to detect, for example, proton-neutron collision or proton-proton collision, is of the order of a few millibarns. Millibarns means 10 to the minus 12. Okay, and picobarn is 10 to the minus, millibarn is 10 to the minus 3. Few millibarns is a typical cross section which can be easily detected. And picobarn is 10 to the minus 12. Fantastic. course the experiments have the capability, the detectors can detect such things. Now let me understand the lines. Now this is the topmost line is the total cross section. That is, if anything happens, here is the energy of the center of mass energy. For a collider, the center of mass energy is the lab energy. You have to focus on this value 8 TeV, which is the energy with which the LHC operated, proton-proton collision at a center of mass energy of 8 TeV until the year 2012, and this is the energy at which it is now operating. Well, not really, this I believe is 14 TeV. Now it is a little less, 30 TeV. Can you tell us that when 14 TeV is supposed to be realized? Is there any projection?
No, it's probably in the super LHC.
Maybe the next shutdown.
Yeah.
Alright.
Up to 2008.
It doesn't matter, 13 or 14 doesn't matter. Now here, this is the total cross section at 10 to the 11 picobar. So this is almost, how much? 1 bar. Little less than 1/10 of it. And here is the Higgs production cross sections. Now you will hear more about it, but this is the production of a single Higgs via gluon-gluon collision. You will understand how gluon-gluon collision happens at LHC. And here are other production channels. Here it is produced in association with the WZ. But by and large, these cross sections at 8 TeV where Higgs was discovered in 2012, where it is less than even the best one. You see the blue one, it is a little more than 10 picobar, a few times 10 picobar. So the probability of producing a Higgs via the best production channel, which has the largest cross sections, others are far below. It is the ratio of something like a few times 10 divided by 10 to the 11. So it is really a needle in the haystack kind of situation, that you have huge number of events, out of which a tiny fraction will be Higgs, and you have to detect it. But the good thing is that theoretical calculation gives you the number. So if you the number of Higgs events matches on the basis of calculation made in the standard model, then you can see that it agrees with the standard model. The number of Higgs event observed agrees with the number of Higgs events predicted by the standard model, and therefore you have the confidence that you are indeed seeing the Higgs.
Sir, as you mentioned that there is a first issue of production of Higgs and then it decays to some.
I am coming to it.
So just to clear the nomenclature, when we see these plots, this is that Z and H. There is one line with Z and H, or HH or TT bar H
Okay.
basically. So
All
if
right.
you can explain what that nomenclature is.
Yeah, I'll come to it. See, it means that even if you forget about the total
Right.
thing, what is the production cross section of a W? This you will hear much more in details later on, how is W produced and so on. But on the face of it is 10 to the 5. So it itself is 5 orders of magnitude more than the Higgs production, the best Higgs production cross section. This, for example, is Z, little less than W, but still it is substantially large, a few times 10 to the 4. So even if you forget about the total cross section, most of which will be rubbish events anyway, soft scattering as you call it, which does not carry any particular information about anything, except for the fact that the proton is a complicated object. There is no other information is. But even these cross sections, this other blue, etc., BB bar, I think this you will need in the next slide. This cross section is how much? This is a few times 10 to the 8, huge cross section, a B quark and B anti-quark produced in BP collision. So So these are all huge numbers. So this is needle in a haystack. Then as he was telling, this is not the full story, right? This is only half of the story, that is the probability of production. But next comes the probability of decay, and we have to spend some time on it. But before that, let me just introduce a definition. I am sure many of you know that most of the particles decay via multiple channels. That means the final state is not fixed. Now, according to the standard model, the Higgs boson, for example, can decay into, let us say, BB bar and a real Z and a virtual Z. Again, what is a virtual Z will be explained later on. Therefore, if there are multi-channel things, then the probability is defined by suppose a particle decays into particle A decays into particle 1 and 2, and the same guy decays into particle 3 and 4. Now, each decay has a particular probability, which is called, each of these is called a partial width of A, and the ratio is called, not the ratio of the two, I am coming to it. This is called a branching ratio. So if a Higgs boson is produced, it has a certain probability that it will decay into the channel 1 and 2. Similarly, there is another probability, which is that the particle produced decays into particle 3 and 4. And in each case we can define a branching ratio. And this gamma, however, is the width of the pump. That is the total decay probability. So obviously this gamma is nothing but obviously the sum of the branching ratios should add up to the total width of the total probability. Now again, these things can be calculated for the Higgs boson in standard model. And what information do we have? Where is the Now what do you learn? Now you can forget about all the points on the x-axis because this is the variable mass of the Higgs. When Higgs was not discovered, this picture was drawn. You can forget about it. Now we know that the Higgs is at about 125 GeV. So somewhere here. So you see that obviously the probability that Higgs decay into a B quark and its antiparticle is the largest. And from the y-axis you see that it is almost 1, right? More than 90%. So a 125 GeV mass Higgs decay into branching ratio of Higgs decaying into BB bar is Well, more than 90%. Okay. So I write roughly equal to 90%. A little less than probably 90%, not more than 90%. A little less than 90%. Then why the hell did we look into Higgs decaying into two photons? Because probability bigger should be our goal, right? So where is it? It is going to two photon. Well, here, for example, it is a few times 10 to the minus 3.
Almost 2 orders, yes. Okay.
So why did we choose it? Why did we choose it? Is it stupid? What about the other one, Higgs decaying into a Z? Oh, it's not here, no, it's here. So Higgs going to ZZ. Here we find that it is slightly better. It is here a few times 10 to the minus. So why did we choose these two? Well, underlying this choice there is a very important issue in collider physics. A issue which we encounter in our everyday life. Just think of your, maybe here I will chat a little bit. Just think of our everyday life. You are watching a TV and what you are seeing is the signal that is reaching your TV from some broadcasting station. But quite often, in particular in a rough weather, what do you see? You see that there is a very, very imprecise image. You may hear spurious sound. Now the chatting mode is this, that I grew up, let us say a little more than 50 years ago in my life. I grew up listening to radios. TV was out of the question. And there one could really appreciate what is a noise.
Right.
The reason is, if you have a DC radio in particular, which was the case in Kolkata, again you are listening to a radio signal. But suppose somebody is running a defective pump in the next house. Then what happens? The pump will give sparks, that is electromagnetic radiation, and they will be caught by your radio antenna and you will hear tremendous noise. In TV, most of the time it's a mild disturbance. In the case of radio, the whole signal will be impossible to hear. So this is what a noise. And in the case of a collider experiment, it is the same. When you are searching for the Higgs signal, for example, Higgs going to gamma gamma is a Higgs signal. That is the signal. But there is a tremendous amount of noise which is the background, and if that is killing, then you will never see the signal. The signal will be completely obscured by the background. And therefore, if you go back to the figure over here, you will see that Higgs going to BB bar has a large branching ratio. But look at the production probability of BB bar. It is sitting at a few times 10 to the 8. Whereas the Higgs production, the poor Higgs is sitting somewhere here, this blue line, which as I told you is a few times 10. So even if a small fraction, this BB bar is also quantum mechanics. So there is no reason why arbitrarily produced BB bar will have a peak at the Higgs mass. However,